Hi, I'm Ella from Imperial College's Nanoanalysis Group. I'm going to be speaking today about a molecular structural probe for in-situ biosensing applications using PEDOT PSS OECTs in particular. And then I will also go on to other applications of this advanced structural probe, looking into accumulation mode OECTs and gas sensing devices. So I'd like to quickly introduce the OECT, the Organic Electrochemical Transistor, before getting into the specifics of our work. As many of you may be familiar, the OECT is a 3-terminal device that is similar to an OFET in configuration. However, the main difference is that the OECT uses an electrolyte with mobile ions that penetrate the bulk of the polymer film. And these ions can actually electrochemically dope or de-dope the film by counter-ion pairing with holes or electrons. So the most popular material used for OECTs currently is PEDOT PSS, and this conducting polymer works in depletion mode where it's initially on and switched off by gate voltage via electrochemical de-doping. It's achieved transinductances of millisiemens and high response times of tens of microseconds. So other materials such as accumulation mode polymers have attracted a lot of attention due to the initially off state, which switches on at a gate voltage or an analyte, and that allows for lower power usage and tends to be more sensitive to the detection of analytes in biosensing. Within OECT biosensing applications, there are a few various forms of sensing, including neurological, impedance, and analytes such as metabolites. All of the above currently relies on electrical current changes, so it's an amperometric method of detection. And although this has been essentially a widely used probe for biosensors, this method tends to have its challenges. One is that it tends to limit sensitivity to quite low current changes, nanoamps to microamps, and the selectivity in complex cell media tends to be quite low. This is because of components that influences the current, and in the case of new sensing, identifying mechanisms or interactions of analytes is difficult with just electrical changes. Taking into consideration the limitations of amperometric detection, we introduce Raman spectroscopy as a structural probe. So Raman is a vibrational spectroscopy technique, and it is sensitive to pi electron density. This is influenced by changes in the material's chemical and electrical properties. Therefore, it's actually highly applicable to conjugated polymer systems such as PEDOT PSS, which have a lot of pi electron density and changes in polarizability. So before applying this structural probe to sensing and OECTs, we can first build a database of structural changes upon electrochemical doping or de-doping. And this is done in an electrochemical cell that is operated under a Raman laser simultaneously. So we can establish signatures of nanoscale structural changes during electrochemical processes. So PEDOT PSS has distinct structural changes depending on oxidizing or reducing applied potentials, so electrochemically doping and de-doping the film. And this changes the structure between quinoidal and benzoidal. So there are actually certain vibrational modes that are affected the most due to the doping level of PEDOT PSS, and they are assigned to the main conjugated backbone. So by choosing an excitation wavelength that is resonant with a neutral pi to pi star transition, these spectral changes are particularly sensitive to the neutral segments of PEDOT. And the spectral features can be quantified based on certain things like full width half maximum, relative intensities of peaks, and peak position. And these are tabulated on the right here. And we can see that there is a distinct difference between the reduction and oxidation regime for all the spectral features, which means that there are certain signatures corresponding to the electrochemical doping and de-doping of PEDOT PSS. So now that we've built a database of signatures for electrochemical doping and de-doping of PEDOT PSS, we can then apply this structural probe to operational OECTs for biosensing purposes using the reference signatures that we've had before. So to start with, we demonstrate a simple enzymatic glucose sensor in PBS phosphate buffered saline solution, going down to a concentration of 0.02 millimolar of glucose. We directly probe the structure of PEDOT PSS in the OECT channel while operating the OECT. This means that both the electrical current and structural changes are recorded simultaneously. And upon glucose addition and completion of this electron transfer cycle, the gate electrode efficiency increases, which decreases the current even further, and this also dedopes the PEDOT PSS, so we see that in the spectral changes. So moving on to comparing the two probes against each other, we can see that the electrical current is actually significantly reduced by the preconditioned stages, where other components such as ferrocene affect the current. On the other hand, the spectral changes are fairly stable, or they produce opposite signatures to the glucose sensing regime, where PEDOT PSS is further dedoped by the glucose addition. So we can conclude here that the structural probe is actually unaffected by the other components in the electrolyte and is just as sensitive to the analyte detection down to 0.02 millimolars in PBS. So in a similar way, we can use another experiment to test the selectivity of the structural probe in physiologically relevant environments by using complex cell media as the electrolyte. So the addition of ferrocene alongside the other electroactive components that exist in the cell media causes a significant decrease to the current, nearing 0 amps, limiting the sensing to only about a microamp. Meanwhile, the structural probe is actually highly selective to the sensing regime. There is opposite signatures to when the PEDOT PSS is further dedoped by the glucose, and it's also fairly stable throughout a long period of time. There is also a full recovery to many of the spectral changes after washing. So what we see here is a structural probe that can be used simultaneously with the amperometric method of detection, but is more selective and sensitive to the active material, PEDOT PSS in this case, but this is also highly applicable to other conjugated materials. And that's what I'll be speaking briefly about. Our other work, which has used this advanced structural probe for materials such as P3HT, PBTTT, and DPP-based polymers for accumulation mode OECTs. In this work, we showed that by adding DBSA in a 1-to-1 ratio with TVA-PF6 salt in electrolyte, the OECT characteristics are improved. This includes transconductance values as well as V-on values and the drain current magnitude in particular. So actually for P3HT, I think this was the highest recorded transconductance at the time. So to investigate what the small molecule additive DBSA was doing in the electrolyte, we actually applied the structural probe in a similar way to the PEDOT PSS study. In this case, it's resonant with a polaron, so polaron signatures of P3HT are established by using in-situ electrochemical Raman. And this was compared between different electrolytes, so with and without DBSA. And we find that the signatures actually show reversible electrochemical doping. We can see here that at 0 volt there is no polaron signatures, but only with an electric field and oxidizing potential there is polaron signatures, and this is fully reversible. However, DBSA on its own, without another salt in the electrolyte, actually irreversibly chemically dopes the polymer, and this is seen here in the spectral changes where even at 0 volt you see a polaron signature which remains during and after the electric field is applied. So in another application of the structural probe is a study of P3HT and solid-state ion and liquid-based blend systems, and this study revolves around chemiresistors, which are two-terminal devices made to sense VOC gases. In this case, the solid-state ion liquid is actually mixed into the film with the P3HT, and this increases the current significantly, but also enables the sensing capabilities of the device. So by using the Raman structural probe, similar to before, the P3HT can be actually biased electrically in solid state, not electrochemically, and we can see here that polaron signatures are actually only seen in the ion and liquid blend. So by comparing the spectra to the electrochemical Raman study, we determined that it was indeed reversible electrochemical doping of P3HT by ionic liquid molecules in the solid state, driven by the electric field. So moving on to the gas sensing devices, we can now expose the solid state ionic liquid chemiresistors to the VOCs, and we see that there is a dependence on the polarity of the VOC. So acetone and toluene causes different changes in the P3HT. And therefore, we can hypothesize a sensing mechanism based on the electrostatic interactions that change the P3HT's structural and electrical characteristics to determine how acetone and toluene are interacting with the polymer and ionic liquid. So to conclude, I have spoken about the development of an advanced structural probe using Raman spectroscopy for in vitro biosensing applications. We show that this technique is actually very complementary and can be used on operational OECTs for both types of analyte detection, where this probe really shines its sensitivity and selectivity, as it is only probing directly the active material changes. And I also showed other works that apply this structural probe to accumulation mode materials and VOC gas sensing, where we can use this probe to identify specific interactions and mechanisms. Thank you for your kind attention. I'd also like to just acknowledge UKRI, CPE, and all of our amazing collaborators, and of course the Nano Analysis group in Imperial. Thank you.